Swayam Prabha. Digital India. Educated India.
Now, what we need to also show is that these increases are sort of relatively controlled. So, as this alpha t grows bigger and bigger, I should not run into the problems that I talked about earlier, right. So, I need to show that next. So, let us state that proposition. So, here the proposition is that for any t, okay, alpha t plus 1 is less than equal to alpha t plus 2 square root n. So, we will see how to use this. Okay, so, let us prove this. So, this is just rewriting what we had before. Okay, and I claim that this is less than equal to n minus 1 over n beta t. Can anyone justify this for me, this inequality? When does this inequality hold? When alpha t is positive. So, why can I claim that alpha t is positive? Okay, so fine. So, yes, so alpha t is positive, so therefore I can make this claim. Okay, so fine, so far so good. Now, we also know that n minus 1 beta t the whole square is less than 1, right. This just follows because the amplitude should sum up to 1 and I did not even consider alpha t. So, I get that beta t is less than 1 over square root n minus 1. So, this is just simple symbol pushing. So, what does this give us? So, alpha t plus 1, which we compute as 2 mu t plus alpha t, right, by definition. So, let me write that part again. So, alpha t plus 1, which we said is equal to 2 mu t plus alpha t, okay, is 2 n minus 1 over n beta t plus alpha t. So, this mu t bound we got previously, right. So, we are just substituting that and now good. Now, we will use the bound on beta t that we have, right. So, we will get 2 n minus 1 over n 1 over square root n minus 1 plus alpha t. So, I am just using those simple bounds that we derived before, yeah. Any questions? Just the bounds that we derived, simple ones, right. So, you remember, so here we had a bound on beta t, right. So, we are just substituting that. So, here we have a bound on mu t and then we also have a bound on beta t. So, we are just using those. So, yeah, so we got this far and we just used a little bit of simple algebra. So, let us keep going. So, this further can be simplified to 2 square root n minus 1 the whole divided by n plus alpha t. Okay. So, yes, so this can be written as less than equal to 2 over root n plus alpha t as desired. So, we proved these two bounds. Okay. So, we showed with the first proposition, we showed that you know, as long as alpha t is bounded above by half, I will make progress with, you know, at least steps of 1 over square root n. And the second proposition showed that you know, alpha t plus 1 is always going to be bounded above by alpha t plus 2 over root 2n. So, this will actually suffice for us to conclude the proof. Okay. So, let us do that. So, using this let's you know, we will pick a constant and we will show that that you know, we will get alpha t to be at least that constant after sufficient number of steps at some t. Okay. So, let us, so now we show that alpha is greater than, let us say 0.1 after order square root n steps. Okay. So, we will show this. So, first I claim that if n is less than 16, then you know, alpha t is 1 over square root n, which is greater than equal to 0.25. Can anyone tell the class why this is? Okay, you can check it later. So, you can check this. Okay, good. Now, if n is you know, greater than equal to 16, as long as t is greater than square root n over 8, we are going to get alpha t is less than equal to alpha 0 plus 2 over square root n times t. Can you tell me why we get this? So, look at the propositions which we showed. So, do you see why we get this? Okay. So, I am just sort of applying the proposition again and again, right. So, I will apply it t times. So, I will get this. Good. So, this is less than equal to alpha 0 plus 2 over root n over 8, right. So, this is 1 over root n. So, alpha 0 is just 1 over root n plus 1 over 4. Okay. So, this is less than half. So, this means that for root n over 8 steps, I can keep growing by 1 over root n, you see. So, what did we show? We used the second proposition to show that for so many steps, I am going to maintain my amplitude to be less than half, and this was the condition for applying the first proposition. Okay. So, let us now apply the first proposition and see if we can conclude. So, by the first proposition, for you know, root n over 8 steps, I can get alpha, you know, root n over 8 greater than equal to root n over 8 1 over root n, right, which is 1 over 8, which is greater than 0.1. So, the step size is 1 over root n, and I am doing this root n over 8 times. if you want, you can look again at this argument we made previously. So here what we showed in this in this part is that if my number of steps are upper bounded by root n over 8, then I computed that my alpha t will be upper bounded by half. And this was the condition that I needed to apply the first proposition. Remember, we said that if the alpha t is less than half, right, then in each step for how many ever steps the alpha t remains less than half, I make a good increase of 1 over root n in each step. Okay. So that means now that we showed that for root n over 8 steps it remains upper bounded by half. So that means that for root n over 8 steps I will increase by 1 over root n in every iteration, right. So that means the total increase is how much? 1 over root n times root n over 8, which is 1 over 8, which is fine. I mean, it is some constant. So yes, I mean, as usual you can amplify this probability. So note that, look, if this is the alpha, then the probability of getting x star is only square of this, right? Right. So this is, it's whatever, it's greater than 0.1 squared, right. So this is 0.01, this is pretty small, okay. But if I repeat this process many times, so let us see, so suppose I repeat this a constant number of times, let us say 110 times. So 110 just makes the calculation simple. So then the probability that one answer is x star, right, is the probability that 1 minus the probability that of not x star, right. So this is greater than equal to 1 minus 0.99 to the 110. So 110 is simply chosen because this gives you 2/3. And 2/3 is good enough, obviously. So I wanted us to do this analysis a bit carefully because just looking at the intuition is not enough. I mean, things can go wrong. So we need to ensure that those things don't happen, and we did it in a very careful way. So we argued that as long as the amplitude doesn't grow too much, it still keeps growing well. And then we argued that by the time it is growing well, it gets to a point which is at least constant, and then we can repeat many times. So once again, the quadratic speed up offered by Grover's algorithm is very important, right. So because remember, I mean, you only shaved off a factor half, but this half is in the exponent, right. So this is a huge speed up, and if I apply this to cryptography, as I already said before, I mean, this question is so general, right, this unstructured search in a database, this question is so general. You could think of searching for a cryptographic key in the space of all possible keys, right. And now you are saying with a quadratic speed up, so shaving a factor half in the exponent, basically what you are saying is that the bit security of the key is actually halved, right. So if my key is whatever n bits, it should take me 2 to the n time to search for it, right. Now I am searching in 2 to the n over 2. So this means that effectively my key size is only n over 2. So to get the same level of security, I need to double the key length. And this algorithm has led to that, so for post quantum security now, we do think that, the key length should be doubled. So this is a very big implication. Okay, so it is still not, it is not like a complete break, but it is still very significant. So let's end here.